Welcome to the mill setup video. We're going to take a look at four things in this video. Number one, how to check to make sure that your head and vise are trammed properly. Number two, turning on your controller and making sure that it works as a DRO. How to install a collet and a sharp tool into it and doing that carefully. And then how to install your actual part into the vise. So let's get started. How to check to make sure that your head and vise are trammed. Let's hear what Don has to say about this. All right, welcome to our mill video number 2 at the Brighton campus in our prototyping lab. Don Howard, myself, John Waddick here. Don, we've already gone over all the parts of the machine. My head is spinning. I'm going to have to study that first video a few times, but you did a really good job. Thank you very much. Today we want to get and show people how to set up a part, get it ready, get the machine all ready. We're going to do pretty much everything we need to do except actually machine the part. So what's the first thing a student would have to be aware of before starting a job?
One of the first things you need to make sure a typical machinist would do is make sure the head was trimmed, especially if I'm walking up to a machine that I haven't ran before. We talked about these components, this knuckle, before. If this head is out of tram, we call that tramming when the head is perpendicular to the table. If that's out of tram, you will get a bad part, or you get things that are not square. So it would typically be done before you guys came in for your 153 students that don't have to be involved with that.
All right, so just to kind of tell you, the tramming is we want to make sure that this spindle is absolutely perpendicular to the table. Am I correct?
That is correct.
All right. And, you know, if the things on the knuckle and the head were not aligned properly, for instance, instead of getting a straight drilled hole, we might get one at an angle. Okay, so we don't want that. So to get good machining results, we may need to make sure that the spindle is absolutely perpendicular in two directions, okay, in two planes. So that's hopefully done already for you.
That's correct. Typically our engineering students wouldn't have to worry about that. And the other thing you would lead into is your vise needs to be square to your axes. All right.
So this is the vise.
This is your machinist vise. The machinist vise is a precision vise. This is your solid jaw. You'll hear me refer to it throughout the videos.
Why is it called a solid jaw?
It doesn't move. Okay. All right. It's solid. It doesn't move. It's your precision vise. It's one you rely mostly on. So what you do is you'll have an indicator will be run across here until a red zero with this axis, the x-axis. All right.
All right. So let me just, if you turn this thing, all right. So this is the movable jaw?
Yes, this is your movable jaw.
Okay.
All right.
All right. So we need to tram this also, but once again, this is going to be done, and like Don said, tramming of this vise is to make sure that this fixed jaw is absolutely parallel with the table.
That is correct.
Okay. Now, we're going to hope that that was already done for us. If you have a question or maybe your part's not coming out right, Don, should a student just start to get a wrench and go to it?
No.
Okay.
You want to check with your instructor, especially if you haven't been instructed on how to tram a machine. Just don't come over and start messing with levers and screws and bolts and trying to change it and make adjustments. You'll end up with a bigger mess.
Okay, that's what I thought the answer was going to be. Alrighty, so we're assuming that the head is trammed, which means perpendicular, and and that the vise is trammed, which is the solid or fixed jaw is parallel to the table. All right, so assuming those are done, Don, what's next? Let's review what Don said about how to check to make sure the head was trammed and a vise is trammed. If the head is trammed properly, then the axis of the spindle will be perpendicular to the table. That'll be hard to tell by eyeball. Now the good thing is your instructors at the Applied Technology Center will be checking this over to make sure this is set for you. But if you find or suspect that something isn't right, something looks tipped, or your part's not coming out right, you're going to want to ask your instructor to check to make sure that the head is properly trammed. It's also important for the vise to be trammed, and what that means is if it's properly trammed, the jaw or the fixed jaw, or what Don called the solid jaw, would be absolutely parallel to the grooves on the table. All right, so those are two important things. Make sure that the spindle axis is perpendicular. I don't know why that came up, but and then also make sure that the fixed jaw is parallel to the grooves. And like I said, if either of these things you suspect are not the case, you need to ask your instructor. Don't just grab a wrench and start trying to fix it yourself, because like Don said, you could cause more of a problem. Next, let's look at turning the controller on and making it work as a DRO.
Well, the next thing I would do is I would turn on my machine just so I can get my DRO turned on.
Can you show us how to do that? Jason, can you?
I'm going to flip the switch.
All right, he's flipping a switch.
Right. And it'll turn on my computer.
So Don, this is a whole computer right in this.
That is correct. It's a computer.
It looks kind of like my computer starting up.
It is. Basically what drives this is a Windows operation.
Oh, it's got Windows XP. We're right up there. Okay.
Mm-hmm.
All right. So as that's coming on, Don, once that's on, Don, that means that the controls on the machine will now begin operating. You can turn the spindle on and do other things.
That is correct. I can use power feed. So in order to get to power feed, where I can manipulate my machine under power, I would have to go to mode. I'd have to go to DRO, which is your F1 key. And now we're back to our XYZ 0 screen, where we see jog, power feed, do one, teach, ABS, and tool number.
Okay, so the power feed is the second one over. I also see something called jog. I know we'll get into this in a later video, but those will essentially move something.
That is correct.
Okay. So the important thing is we've turned that on.
Let's review how to turn the controller on and make it work as a DRO. First off, you need to flip the power switch upward, and that switch is on the side of the controller. After you do that, the screen will go through a startup. Windows XP is run on most of these machines, and when that startup is done, you then can press the mode button. It's on the right side of the screen. When you push the mode button, then there will be a bunch of choices at the bottom of the screen that you choose by using the function keys, and you'll want to press the key right under the thing DRO. When you do that, then the X, Y, and Z coordinates of the tool will be shown. Let's next look at installing a collet and then properly putting a tool into that collet.
All right, and what's our next step?
Our next step is we have our spindle on. I want to set up my machine. Obviously I'm going to determine what kind of work am I going to be doing on my part. All right. If I'm just doing straight end milling, I'm going to have to choose the tool that I'm going to be using. I'm going to have to get the collet for that tool. I'm going to have to insert it into the spindle and set to get parallels, and we're going to go through each one of these steps right now.
All right, so Don is going to he's grabbing a tool. Now, Don, you are an experienced machinist who knows the care of holding a cutting tool. Now, engineering students, I don't recommend that you hold on to the end mill with your bare hand. I mean, Don, he's got a paper towel. These things called flutes.
Cutting edges here. They're cutting edges. This is your cutting edges, and these are your flutes where the clearance is. You generate these cutting edges. All right. These cutting edges are going to cut metal, so your flesh will cut that much easier. So if you're not confident, you should not try to handle these tools with your hands. All right, with your bare hands, because they will slip. If you're trying to pull on the collet and your hand slides just the slightest, you will be cutting your fingers. All right.
Wow. Okay. So we want to be careful of that. All right. So just so you can see better, Don, if you don't want to use the paper towel, if you I think we got the permission slip from your mom that says he can cut himself and we don't care.
As long as you keep a close eye and watch out. Take care of her little boy.
All right. So you've got something over here. So this is called an end mill. It's a 3/4 inch end mill. Has cutting surfaces both on the bottom and the sides. Got to be careful. I'm touching it not on the silver, or if that's gold, I'm touching it on the silver. All right. So now, Don, what are you doing over there? You're unscrewing something.
Right.
Did anybody give you permission to do that?
Not yet, but I'm trying to get advanced.
Okay.
So my curiosity is, how am I going to get that tool in to hold up into this spindle? Well, there's a nut on here that holds the collet, which is the same size as the shank of the tool. And it
Wait,
gets,
could you show the collet again? So this has lots of lines in it. The one over for the lathe only had like 3 of them. Why so many here?
this is a precision collet, and this is allowed to collapse around the whole shank very nicely.
Okay. So instead of just 3 units clamping down, we have, well, I can't count that high, but it looks like 8.
You got probably 16, yeah, because you got them from 2 directions,
Oh, okay. From the back.
back and the front.
Okay. All right.
It actually acts like a spring.
Spring.
So
Okay.
you move in or out evenly.
All right. So something's going to squeeze this thing to squeeze it onto the end mill.
Right. And when we go to put this in the collar, you can see that these collets have a groove in them. Those grooves have to seat into a ring that's inside here. And the easiest way that I can explain to set this up is there's an eccentric. You can see like an eccentric in here. This ring is offset. It's solid. It's part of this nut that holds all this assembly together. So what you want to do is you want to find the high spot, have it pointed up, take your collet, lay it in.
What do you mean by the high spot, Don?
All right.
Turn it toward the camera.
Okay, I'm sorry about that. See how this eccentric is?
Yeah.
All right. I have more clearance up here. I can see more of the angle, this
Yeah,
the
yeah.
secondary angle, and I can see less of this secondary angle down here.
Okay.
All right. I'm going to take, and that lip is higher up, so that lip that's higher up is going to be sticking up.
Yeah.
I'll take my collet, I'll stick it in, and then I press it in, and it locks in very easily.
Okay.
All
Can
right.
you just repeat that again? So you're putting this collet in at an angle and then snapping it into place. So can you just kind of go over again?
So I got that ring, it's sticking up so it catches into this groove. All right. So I'll take it and I'll lock it into that groove, and then I just snap it in, and that'll hold the collet from falling out.
Okay. Is there any other way to do it?
Yeah, you can try, but sometimes you will struggle trying to get it to snap in. If I try to do it the opposite way, it's hard to get it apart. All right. If I try to put it in this way, now
All right.
I've got to try to collapse that collet far more.
All right, so let's see if someone who's never done it before can follow your directions. I guess this part is where I want to try to put this down because that's closer to the edge. That's the way I'm looking at it. So I'm putting that in there like that, and then I'm pushing up. Oh, I did it. All right. Okay, so if I can do it, you can do it. All right, so Don, now we got the collet in there.
If we don't do that and we just take and push the collet up into the spindle, when you go to take the collet back out, it'll get jammed up in there because the taper that's on here, they'll actually lock up in the spindle and you won't be able to pull them out. All right, and that groove in that ring is to pull the collet back out of the spindle. All right, so it's very important that you do that.
So we have to do this operation. Now he's just screwing it in there just the regular way. Is that the righty-tighty, Don?
Yes.
All right, so how far do you put it in there? Just enough to hold it for now, I imagine.
Yes. I put it in there just enough. If I tighten it up too tight, I won't be able to get the end mill up into the collet. So I slide the end mill up into the collet.
Yeah, how far do you go, Don? Do you go the whole length of the silver there?
You can go all the way up to where the tin coating starts. You don't want to cover up the flutes. All right? You don't want to hang it out here like so. There's typically a notch in a lot of your end mills. You want to come up at least past that notch. See the notch?
Yeah.
All right? And that's usually depending on the type of holders you have. There's different style holders that they would have a set screw and they wouldn't lock in on that flat. Okay?
So the reason you wouldn't want the flutes up there is that's not a good holding surface.
Well, it's not a good holding surface, and then chips and stuff can get up inside your collet as well.
Lots of reasons. Listen to Uncle Donnie.
Now, as you can
Now,
see,
what's this wrench you got now all of a sudden, Don?
spanner wrench. This is to tighten up this nut.
A spanner wrench?
Spanner wrench, yep. I span around the nut, and I lock it. It'll allow me to lock down.
Now, are you holding on to this To keep it from spinning?
No, I'm just basically supporting it so the tool don't fall out. I don't. If I drop the tool out, it's going to hit my vise. It could hit my part. And worst part is if it hits something hard, even if it hits something soft, I can chip the corner. So I want to protect my end mill.
Okay.
And as you can see right now, it's not coming out. I can leave the rag here if I'm concerned about it. But I've gotten this thing so it's starting to tighten up, and my spindle, it keeps wanting to turn or spin, right? I'm having a hard time turning it. Well, I can't reach the brake and hold on to my tool all at once. That becomes an issue. So what I can do is I can hold on to my tool bit, right? I can hold on to my quill, and I can already reach up here and put this in back ears or low range. All right. Now my spindle, remember we talked about having a lot of resistance. So now I can take and I can start to tighten this up. As soon as I start to tighten it up, now my spindle wants to move. I can hold on to my brake, and I can tighten up the collet the rest of the way and ensure my tool is not going to come out.
All right, so using the brake here, Don, at the end is when you really have to crank it down. Putting it in reverse is almost using like a torque wrench where you bring it to a certain tightness.
That is correct.
All right. All right, so while Don is tightening this up at the last step, he uses the brake, and that locks the spindle so then it won't turn while he's tightening up the, what's that called, the collar?
The collet, yeah, the nut.
All right, got the tool in there, Don. We ready to cut? I guess there's nothing in there. It looks like somebody cut that vise. Is that true, Don?
Yeah, someone nicked that vise.
Okay, well, we're going to find them. Remember, they can run, but they can't hide.
Let's talk about how to install a collet and then how to put the tool properly into that collet. First off, you need to remove the spindle nut from the mill. Then you install the collet at an angle, as I'm going to show below. All right, if you look on the front view, which is on the left side here, if you look inside of your nut, you see that there's an elliptical hole. And you want to position this as you're looking at it so that the position where there's the smallest shoulder, this upper part that I have the cursor on right there, you want to have that in the upward direction. Notice in the bottom area there'll be a bigger surface there, and that should be on the bottom. So smallest surface on the bottom. Now, if we turn this 90 degrees so that we're looking at the side of the nut, so this is the side of the nut, we'd want to put our collet in so that it's tipping downward, okay? So you tip your collet so that it's inclined downward, and then you're going to apply some force to the end here and snap this, this upper part back up into the nut. All right, it was demonstrated on the video, but and the same thing for taking it out. You'll want to make sure that you have your collet as you look at it aligned so that this space is on the upward, this narrow space is on the upward, and then you would just pull down on the collet and it would snap right out. And that was the snapping process we were talking about. Now, to put the tool in, you're then going to first screw the nut and the collet hand tight onto the spindle. Okay. Then you should switch the machine into the low range, and this will put some resistance onto the spindle. You can then insert the tool into the collet. So actually, this is where you're going to put the tool in. You're going to hold on to that tool with a rag or a paper towel because it's very, very, very sharp. And if your hand slid across any of those sharp cutting surfaces, you would all of a sudden be bleeding quite profusely. You want to insert that tool up past the notch, and then you're going to tighten the spindle nut with the spanner wrench. Okay, you're going to be holding on to the tool at this point. You're going to just tighten it up just to hold the tool in. You're not cranking down. Once you have it tight enough where the tool is not going to fall out, then you can apply the brake to the mill and that will lock the spindle, and then you can really tighten up that spindle nut. Finally, we have to look at how to install a part into the vise, and Don's going to cover that next.
All right, Don, I assume the next thing is let's just throw a part in there. So you just throw it in there like that?
Watch your hands when you do that.
Oh. What did I do wrong?
Out there and drop this part in here, just like I did, and without thinking, you just want to be excited to get your part in here, start machining. There's safety zone. Let's think of this as a safety zone. We talked about a cylindrical safety zone on the lathe. This also needs to have a cylindrical safety zone. You want to keep your hands away from this cutter at all times. Just this action alone, that's a knife edge. It's sharp enough to cut metal. You sliding your hand in here, if you ain't thinking or you ain't concentrating, you're slicing now you just cut the back side of your knuckles. All right.
All right, that was a stupid thing I just did. Bad me. All right. So I don't do that.
No, you don't.
All right, something's in there. There's that cylinder of safety we have to stay out. All right, so what do we need to do? Don, we want to put a part in. All right, so Don, now you have your part and you're ready to put it in.
I'm going to get the tool out of the way of my work area so that it's not where I'm going to be working with my hands. I always want to work in that safe zone.
Well, that's a good idea. So he just he moved the vise. We actually moved the saddle, I should say, and that got it away from the cutting tool. Now he's moving the table, moving it even further from the cutting tool. Now he can work inside the vise without being in the hazardous zone of that cylinder that we talked about before.
Right. All right. Now I have a part I want to put in here, and I want to be able to have it so I can machine it. But right now I have no control. If I set it in the vise, it just goes to the bottom. There's things we call parallels. The parallels will rest on the bottom of the vise and raise up my part at desired height so that I can establish a plane. And that parallel plane will keep my orientation this way, remembering that my back jaw will give me the orientation of the part this way, right? So I'm saying all this so that I can show you that along with putting parallels in to control stops points, the back jaw is another point. Now we're going to put in a third point, which is a vise stop.
All right, so Don is going to grab a vise stop and parallels.
All right.
Oh, he's got the parallels now. You always use two of these?
Yes, we'll always use two parallels.
These are a match set.
They are a match set.
How do I know they're matched, Don? Do they have like an etching on them or some kind of serial number?
There should be an etching on them over at the Applied Tech Center where you guys we're doing a lot of work. Right here, this one's, you can see that it's etched on here, 1/8 by 1.5 by 6 inch. And the second one is etched the same way. A lot of times they'll have the tools etched 1A, 2A, 3A, 3B, etc.
So from the factory that we got these were precisionally machined to be exactly the same. So if you got different parallels, even though they were both, let's say, 1.5 inches, you don't want to mix a set that you bought once with another set. Is that right?
That's correct.
And that's why at the Applied Technology Center, you're going to see identifying marks that show match sets.
Right. Yeah. So both parallels would have 1A on it. Another set of parallels may have 1B or 2B. So you always look for.
Are there any that are not to be? There's a 2B?
Well, they're always getting ready to be married.
Okay. All right. Okay. All right. So we got the parallels in there. I mean, what are those for, Don? I don't get it.
All right. We talked about you got datums on your part. All right. And this is.
Now, datums are something that are reference points or reference planes.
That is correct. Reference planes. Your 0. All right. And you guys will be working. You use that in Unigraphics or SolidWorks. SolidWorks, where you create a plane to start with. When you start to draw your part, you got to pick your primary plane. 3 points, create a plane, right? Right now we're using 2 parallels to create that plane. To rest my part from moving this way and this way, all right? Now to get the part to stop from this direction, rotation, I have my back jaw, which is considered my solid jaw. We use that as a 0 reference plane always because it doesn't move, it doesn't change. So I can use a number of different size parts. If I was to grab this one, we can see that there's a different part size. I can put that in there. That Y0, that back jaw becomes my Y0, and it doesn't change. I can do multiple parts. I can do multiple different types of parts in the same setup.
All right, so essentially these parallels give you a proper height on each side to support it, because we don't want the part resting down into the parallel or inside the vise, because then this cutting tool may hit the sides. So we want to, are we going to put that in, or we have to put this vise stop in first?
Put this in. But before I did that, I wanted to bring back to our attention is, I didn't talk about it, but you want to make sure your vise is clean. Chips are not your friend. They're never going to be your friend. Don't ever think that it's okay to have a chip in there. Chips, what they'll do is they get underneath your parallels, they get underneath your part, they'll ruin your part when you go to clamp on it, like we've seen in the lathe section, where it actually embedded in the spindle, and we have to stone them out. They actually embed into your parts, they raise up the surface, so you get inaccurate parts. All right? So
yeah, so if you want to be able to machine to high precision, you must have cleanliness. These surfaces have to seat right true to each other. They can't have some piece of dirt or chip or something underneath that. They're going to mess it up. So Don has wiped the surfaces down, wiped the parallels down, and now he's ready to put the part into the parallels. And he's chosen a pair of parallels that have a certain height. Why did you choose this particular 1.5 inch? What are you looking for when you're machining as in choosing parallels?
the one thing we're looking for when we're machining is to make sure that the final surface that we're machining, if we were end milling, does not go below our vise jaw. So we never want to allow this cutter to run into our vise jaw, or else we're going to ruin our tool and ruin our vise jaws.
Okay. All right, so you've now put that in there. Is that where you'd like to have it seat?
That's the approximate location where I'd like it to seat. I got my part hanging outside my vise. The reason I have done that is if I want to machine the side of this part, I will be able to get my end mill below the bottom of the part. So on that note, I would use a vise stop, and that will allow me to get rest all 3 degrees of freedom on this part.
X, Y, and Z.
Well, yes. Of the part. All right. So now, as you can see, I have the stop. I can open my vise and I can slide my part in up against that stop. And no matter what part I put in, that's going to repeat and be my 0. No matter what part I put in, the back jaw is always going to be 0, and the parallels are going to be always 0.
So if you need to take your part out for any reason, you have the vise stop in there, you can get it back in the exact position.
That is correct.
All right. Good thinking. Whoever came up with that idea, was that you, Don?
Sure.
All right. All right. So now you've tightened up the vise, or no? You didn't tighten the vise up. What's he going to do now? He does it hand tight first.
Well, I just did it by hand tight because cranking
All right. All right.
All right. I take my handle. I put my part in the vise. I hold my part down on the parallels. Now, as you can see, down. I have the most force pushing down. I don't have to beat my vise. If you you don't need to take a hammer and beat this. You're down. If you exert weight, I'm a big boy, 200 pounds. I'm putting a lot of pressure down on this thing, okay? You got leverage. Look at the length of this handle. You're putting a lot of pressure on there. You don't have to beat on these handles. You're just going to ruin your vise by driving that job out.
All right, so assuming that he's got a lever arm about 6 inches and he's 200 pounds, if he put his full weight on there, he would be putting about 100 foot-pounds of torque on there, which is probably more than was necessary.
Right. So you don't need to beat your parts with a hammer.
Okay. So if you're a 100-pound person, you put your full weight, that should be enough?
Yes.
Okay. More than enough. All right, so that's the part installation. We put the parallels in there. You tightened up the vise. And are we now ready to do machining in our next video? Is there another operation we have to do, Don?
No, we're about ready to do machining.
Let's review what Don said about installing a part into the vise. He said first you have to make sure that the vise is thoroughly clean. You don't want any chips, dirt, or grease down in there, because when you put those parallels in, they have to seat right down on there without any debris. Before you start to put your part in, you want to make sure that your vise is away from the cutting tool. So you move the saddle with the hand crank, and you move the table with the other hand crank, and you move so that the vise is nowhere near the cutting tool. You want to always stay out of what Don referred to as the cylinder of danger. because you don't want your hand protruding anywhere near the sharp cutting surfaces of the end mill. When you're putting parallels in, you want to make sure that they are a matched set. And you want to make sure that you have parallels of a sufficient height so that when you put your part in and you've completed all the machining and the milling on the top of the part, that the top of the final machined part is still above the vise jaws. That way your milling tool will not run into the vise jaw. Okay, next you're going to tighten the vise while holding the part down. Okay, so you want to make sure that your part is seated down firmly on the parallels, because if you start tightening up the vise and it's cocked upward or something at an angle, the vise is going to hold it like that and you're not going to get the proper orientation. And then Don showed the idea of installing a vise stop, so that if you ever take your part out and you want to put it back in, you have the same reference point. Or if, let's say, you're going to machine multiple parts and you want to be able to use your same DRO setup, that's another great thing about using the vise stop. Let's look at some mill setup questions. Number 1, if the spindle is trammed properly, how must it be oriented? And if a vise is properly trammed, how must it be oriented? Number 2, why must an end mill be handled with a rag or paper towel? 3, use diagrams to explain how to orient a collet so that it can be easily snapped into the spindle nut. 4 says, prior to the final tightening of the spindle nut with the spanner wrench, what must be pulled down in order to fully tighten the nut? And the answer is not the spanner wrench. Number 5, prior to installing a part into the vise, what must be done to prevent the operator from entering the dangerous cylinder of danger? All right, write those up, give them to your lab instructor, and prove that you're ready to use a mill safely.